Welcome back to class 13. We're continuing on into section 4.2 in the textbook. One thing I feel about this textbook is that they have too many versions of pretty much the same equation. But this is the conservation of energy equation right here. And I think they have a little bit too many versions of it. I think that could be a little bit confusing. I guess I wish I had planned ahead a little bit and then used like one equation and just kept going back from it. But we could think of this as being the energy accounting equation, as one of my colleagues used to call it. And it's pretty much the first law is what we're really describing right here, where you have the change in energy between two states. So this is the conservation of energy. And that's going to be equal to the heat in minus the work out. And this is the sign convention that we typically have. A lot of times we're going to move this over to the other side of the equal sign. But not just yet. We're going to also, as I mentioned in the previous video, because we had these types of situation where we might have something within our control volume that could accumulate or deplete mass and energy. Because of that, we might want to think about the change that's within the control volume, I guess they're saying a control mass is what they're describing it right as in this time. Change it with time. And also by taking the derivative, we're also talking about heat rate, and we're also talking about work rate, which is also known as power. Right there. Taking a left turn really quick. There isn't good real flow between here. Remember that one method of approaching all the calculations is to do stuff on a per mass basis. So a lot of times we'll just divide through here, and we're also bringing back the idea that there's different forms of energy that we haven't always been accounting for. We have that internal energy and the kinetic energy and the potential energy. So I don't know why I'm including this equation in here, quite honestly, to tell you the truth. Here I have presented one of their equations, equation 4.7, and notably that they are lumping together. Okay, no, first off, let's note what's being done right here, right? Is we said here's all the energy that's inside the control mass. But now that I said there's a control volume instead, so we've changed what we've been writing, control volume, but they brought everything over here over to the left. So, when we had a 1 over here was being subtracted from 2, you could see that in is now the positive one and exit is the negative one. So it's kind of, we moved this thing over onto this side, except for the changes that were taking place. So it's really the same equation, but it seems to me that could be kind of confusing. And then down here, for whatever reason, the next equation down, they've been writing it out this way, right in here. But the important thing when looking through the book and looking at this equation is this right here is generally going to be 0 for most of the things that we deal with. All right. So I don't think I did a great job. Let me go back to my notes down in here and write down what I think should maybe be the conservation of energy. Let me think about it. When it comes to a rate, right? Notably that the mass flow rate is being multiplied by these different energies. So honestly, for the most part, I would think that we would want to actually probably write this or something like it, except that we write 0 is equal to Q 1 to 2. And I guess maybe, I don't know if I want to write the 1 to 2 because this is a rate minus W right there. And then, yeah, maybe write this summation of, I liked the M dot in and H total in minus summation M dot E, exit times H total exit. And recognize that they're kind of like pushing all of this stuff together into a total enthalpy. I think that's a pretty good equation, but just recognize we are going to do some examples where we put the potential energy and the kinetic energy and the potential energy back in. But for the most part, we're going to deal. When we do that, we're going to compare it to the enthalpy and see that isn't usually that big of a value. So let's see. Do we want to do this next example or another video? Let's see. Oh yeah, this is a sad little tiny example. So we'll continue with this one. We'll do a better example on the next video. Assume we are standing next to the city's local water mains. All right, so we will be here's the water main. I like drawing pipes like this, by the way. It makes it look like really cool. And so here's the water main. And the liquid water inside has a flow 600 kilopascals in here. So if we had a gauge right there, that would say it would be 600 kilopascals, which is, they're pointing out that's just about 6 atmospheres. And with the temperature, let's see, the temperature is 10 degrees Celsius. And we want to add a small amount of water. Why? I don't know. We want to add a small amount of water. So here's like a little tube that we're putting in here. We've put it up onto the side, and it's 1 kilogram of water. For some reason, we want to add 1 kilogram of water, and we do it with like this, like kind of and a valve mounted on the side. I guess let's put a valve right there. There's a valve. Not a very good looking valve. We should put like a valve stem on it too, right there. There you go. Okay, so we got a better looking valve coming in on the side. So how much work is involved in trying to put something in here? Well, I just, for my own benefit, I said, well, how would they do that? Well, I don't know. Maybe you have some type of device right here, like a little plunger, and we put like a little chunk of water and we stick it into the thing, right? So we're applying some force onto the plunger, which is going to be the work. So how much work is involved in doing this right here? Well, remember that work is going to be the integral of P dV, right? So I'm going to change a chunk of water and move it a certain volume of it and change it against the pressure that we're putting up against the thing. I don't say what our pressure has to be, but it has to be more than 600 kilopascals, because you can't flow from low to high. You got to go from high to low. So we're going to say that it's going to be a little bit larger, but we'll just go ahead and use 600 kilopascals for this. And so we want to have like sort of a volume being pushed in. And so what is the volume that's going to be pushed in? Well, it's going to be really the mass times the specific volume. So we could look up and the specific volume of water. Well, we could actually just estimate it. This is a pretty good estimate of what the specific volume of water is. Another thing to keep in mind is it's about 1,000 kilograms per cubic meter, right? So that's just the inverse of each other. That's what typically for what water is going to be. So we'll go ahead and use that. So we'll say that the work in is going to be, and we don't really know the path during this process. They didn't say it was a constant pressure process. We didn't say anything about it, but we're going to try to estimate how much work is going to be put into the thing. And so what we would do is take pressure times the change in volume, or I guess the change in volume of this thing that would be moving in, which would be, it's going to be equal to pressure times the mass times the specific volume. Right? And you could just use units for this if you wanted to try to work your way through that this was what we were working on. I'm not really sure what the usefulness of this example is, to tell you the truth. I'm I'm not going to lie to you. But let's keep the units correct. We would take 600,000 newtons per meter squared, right, for the kPa, 600 kPa, and the mass is 1 kilogram, and then we're multiplying it by 0.01 kilograms per cubic meter, right? So take a look, the kilograms get out right there. The meter squared gets out from right. I wrote that wrong. My bad. Cubic meters per kilogram. Did I write that? No, I got it wrong. I got it right over there. Right. So yeah, there the kilogram. Yeah, kilograms go away. This here, numerator, denominator. Yeah, and that gets rid and it gets rid of one of those. So we're ending up with Newton meters. So the work that's being done right in there ends up being 600 Newton meters, which is really 600 joules. So, if you wanted to use that instead, or since we do so often, you may go 0.6 kilojoules. I don't know if this was this example was really enlightening at all, but it's in the book. I decided to include it in the notes. I don't want to make fun of it too much. See you in the next example, I think. Let's see. Double check. Because the examples get a little bit more difficult. Yeah, I picked some other ones out right here. See you soon.